Printed circuit board traces are the conductive pathways on the board responsible for transmitting electrical current between different electronic components. They are portions of the copper foil that remains after the etching process. In PCB design, tasks such as routing traces and calculating trace impedance are crucial, demanding careful consideration of various trace-related factors. One such fundamental aspect is the PCB trace width. The PCB trace width is the horizontal measure of a trace, distinct from its thickness, which denotes the vertical dimension. In trace width design, considering current capacity is essential to avoid issues like increased resistance and voltage drops. This capacity dictates how much electrical current a trace can effectively handle without undesirable consequences. While there isn't a standardized criterion for determining trace width, several factors can guide the selection of this crucial parameter. Board layer and thickness. The thickness of the PCB substrate directly influences the electrical and thermal behavior of traces. Thicker boards, particularly in multi-layer configurations, may require wider traces to effectively address increased current carrying demands and optimize heat dissipation. Copper thickness. Thicker copper layers contribute to a more conductive pathway in a PCB trace by exhibiting lower resistance. According to Ohm's law, where V is voltage, I is current, and R is resistance, lower resistance results in reduced voltage drop across the trace for a given current. This reduction in resistive losses allows for the transmission of higher currents without excessive heating. The implications of this extend to maintaining stable and accurate voltage levels throughout the circuit. The enhanced current carrying capacity not only improves the overall performance of the circuit but also contributes to improved signal integrity and longevity. Here is a correspondence table between copper thickness and trace width. Component density and placement. The arrangement and density of electronic components on a printed circuit board significantly influence trace width. In high-density areas where components are closely packed, it is more often opt for narrower traces to efficiently navigate the limited space and accommodate the proximity of components, minimizing the risk of interference and crosstalk. Conversely, in low-density areas with more spread-out components, wider traces may be employed to harness available space, reducing resistance, and facilitating efficient signal transmission. Trace clearance. At PCB way, the default minimum trace width and trace spacing parameters are both set to 6 mm. However, you have the flexibility to customize these parameters within the range of 3 mm to 8 mm. It's essential to stay within the manufacturable limits, as opting for values below these limits could result in challenges such as short circuits, limitations in solder mask coverage, and constraints on component placement during assembly. The recommended minimum distance between the trace and the board outline for optimal manufacturing is 0.25 mm. If this parameter is set smaller than 0.25 mm, there is an increased risk of cutting into the copper during the outline profiling process. The recommended minimum spacing is 0.2 mm from a non-plated hole to a